I have with me Simon Ritter from Azul. He's the Deputy CTO of Azul, and Simon's going to be doing most of the talking, but I thought I would be remiss to just throw him in the deep end. So I thought I would talk first about some of the, I guess, the background behind our partnership with Azul and Opti-Num Solutions. For those of you who do know us, we have a very long track record. We've been in business for nearly 30 years now, and we have, for most of that time, focused primarily on the algorithm development side of the value chain. And that long track record with analytics has mostly been around MathWorks products, but we've also worked in other languages, with other technologies. And as over those 30 years, we've seen an increasing need to deploy the models and the applications and the algorithms that people develop, both quickly and at scale. And the reasons for that is that models and applications are impacting the business more. And as they do so, the need for trust across that whole model lifecycle is increasing. It started with development, and the development phase of a model's lifecycle has, for many years now, been dabbling with issues around trust. We believe MathWorks products provide the best platform for increasing that trust while you're designing the algorithms, but that's not why we're here today. We're here today because the need for that trust is moving more into the deployment and the operationalization spaces. Where's that need come from? Well, a lot of it is mandated by industry, particularly financial services regulations and in safety critical applications for engineering. But increasingly, it's becoming mandated by competitive advantage. If you can adjust your models, if you can deploy your models at scale with trust more quickly, you have a competitive advantage over your peers. But it's also being mandated by social pressure. For example, explainability in AI is a very hot topic at the moment. And explainability requires you to have a tremendous amount of trust in the algorithm that you're deploying. For MathWorks products, we have a lot of trusted platforms for deployment. For MATLAB algorithms, there's the MATLAB production server if you want a performant deployment, but there's also the MATLAB compiler, which takes those existing algorithms in MATLAB and deploys them in other languages and in other spaces, for instance, Docker targets and so on. In the Simulink world, we have Simulink algorithms trusted through Coda automatic code generation, and that enables people to place those algorithms anywhere they like, whether it's in C code or in PLC code or HDL targets, for instance. So we know that for MathWorks products, we have these trusted platforms, but for Java algorithms as well, we've noticed that those are in widespread use in the industries that we serve. The financial engineering, advanced business analytics, and engineering spaces all have Java running somewhere within their ecosystems. And Java needs a trusted platform to run on and to run at scale. We have found in Azul a partner who provides the best in breed with Java platforms. And our decision to partner with Azul is not just because they're best in breed, that helps. But they're also similar in approach to Opti-Num. They're very client-focused. They have a very no-nonsense approach to getting things done. And they focus on supporting their clients through a knowledgeable, responsive technical support infrastructure. And they're here to talk today about trusted platforms for Java implementation. And I can think of nobody better to do that than Simon Ritter. If you follow Simon on Twitter, his handle is @SpeakJava. You'll see that he actually says a lot about a lot of things. And one of those was surprisingly resonant when I checked out his profile yesterday. I'd been chatting to my brother over the weekend who lives in the UK, and he spoke about how the UK had gone completely petrol hoarding mad because 2 petrol stations had run out of fuel. Simon coincidentally posted exactly the same thing an hour before I checked his profile. Rather eloquently, I thought, talking about herd mentality versus herd immunity. But I think Simon talks most passionately and most often about Java. His deep knowledge of the subject is why we thought it would be best to get him to talk to us today on trusted algorithms and trusted enterprise platforms through the Java language. Before I hand over to Simon, just some logistics. Please post any questions that you may have in the chat. I'll be monitoring that. You can also raise your hand. Simon won't be able to monitor that, so I'll interrupt him when necessary. And if we miss you, it's my fault, not Simon's. So over to you, Simon.
Great. Well, thank you very much, Dean, for that introduction. Yes, we live in interesting times, don't we, in so many different ways. So what I wanted to kind of talk about today is to kind of build on what Dean's talked about and that sort of trusted platform, but to give a little bit of background in terms of how Java has changed and why that's led to the sort of proliferation of different choices that we have when it comes to deploying Java. And then I'll talk a bit about what it is that we do at Azul in terms of providing you with a choice and really the best possible options, we like to think, for your applications and how you can deploy your algorithms and so on. So if we think about Java in 2021, it's interesting that Java is now 26 years old. It seems hard to believe, but I actually started my career at Sun Microsystems back in 1996, very much the same time that JDK 1.0 came out. And to think that that was 26 years ago is really quite scary, especially when I think that it wasn't even my first job. And it's fair to say that Java has changed a lot over that time, which is what you would expect. And if we look at the way that things have changed, we had the release of JDK 17 last week. That means we've had 17 versions of Java in 26 years. And that's quite a good number. I mean, obviously we've seen the rate of change over the last few years. And so we've gone from JDK 9 to JDK 17 in quite a fast time. What this has allowed is the introduction of many new language features, thousands of library APIs. And again, if I go back and I think about how many APIs there were in JDK 1.0, and I actually counted them up, and there were 211 classes in the public set of APIs. If we look at JDK 8, which is really what I can kind of consider to be the peak of APIs in Java at the moment, there were 4,500 APIs. So we've added all sorts of things. Now, obviously, we've taken a few away from those since then. So if we look at JDK 11, there was a removal of things like Corba, because very few people use that. And there was some tidying up done. But that's what we've seen in terms of the evolution of the platform. It's not just about adding things, it's also about removing things and making sure that we have the right set of APIs for what we're doing. Talking about algorithms, that also applies in terms of the JVM itself. And we've seen the introduction of different algorithms to the way that we do the things that the JVM needs to do. The idea of garbage collection has changed dramatically. The idea of compilation and the use of just-in-time compilation has made Java a much more appealing platform than it was when it was first released. And aside from the technical point of view, this proliferation of the number of choices that we have has manifested itself in terms of the number of JDK distributions that we can choose from. I liken this to talking about Linux. You have Linux as an open source project, and then there are lots of distributions like Red Hat and Ubuntu and so on. And it's the same now with OpenJDK. OpenJDK is the source code, and we have different distributions to choose from. And we'll talk a bit more about that as we go through. But we can also say that in 26 years, Java has not changed a lot in some other ways. One of those is in terms of its popularity. If you look at the sort of surveys that are done of developers and users and so on, you will find that it's consistently in the top 3 most popular languages. It's also sometimes consistently in the top languages that people dislike as well, which is actually a reflection of how popular it is. Lots of people like it, lots of people don't like it. I think there was, Bjorn Strastrup, who invented C++, who said there are only two types of languages: popular languages and languages that people don't like, and languages that people don't use. So it's sort of, it's saying something that it remains very, very popular. It's also something that hasn't changed is the fact that the Java platform is scalable to internet-sized workloads. That's one of the things that has made it so popular in terms of enterprise applications, addressing those sort of algorithms and so on that we need to deploy. And also the number of people that deploy it. Literally any enterprise company you go to around the world, you will find them using Java somewhere in their infrastructure. Now, if we look at more recently in terms of Java, we will see that things have changed, and we can look at the idea of the OpenJDK and the delivery of the versions of Java. Specifically, looking at the open source project, OpenJDK. This is the source code for the Java platform. And it's quite important to understand what that really means from the point of view of making a choice about which platform to use and which distribution to use. As we've seen since 2018, when Oracle decided to change the speed at which they developed Java, we now have a new release of Java every 6 months, in March and in September. So last week, we got JDK 17. And this has been working really, really well. I think if we just look back over the last 3 years, the number of new features that have been added, the way that that's been done, the way that people have been able to adopt that and keep testing ready for JDK 17 seems to be going very, very well. It's also important to understand that OpenJDK is actually the reference implementation for the standard that defines Java. Defined through the Java community process, something that's been around for a long time. And each version of Java has its own specification request. Again, we'll talk a little bit more about that as we go through. But the key thing about OpenJDK, very important to get across, is that it is only source code. And if you want to use that on your machines, if you want to run your applications, then you need a binary distribution. How do we get those? Well, we can look at the sort of process and understand that. What we do is we start, as I say, with the source code, a project with a repository that has all of the things we need to build a JDK. And the main contributor to the changes for that is Oracle. I mean, Oracle, you can call the steward of Java. They're the people that bought Sun Microsystems. They're the people that acquired the technology through that. They also own the Java trademark, the OpenJDK trademark, and so on. And they have the biggest team of Java engineers, JVM engineers in the industry working on the new features. They're also the ones that make the decisions about which big things are going to be added. But because this is an open source project, it means other people can contribute as well. So Azul does a lot of work. We have engineers who understand about the JVM. Many of them used to work for Sun, many of them used to work for Oracle. And we contribute small things like bug fixes. We contribute small performance improvements, but we also are working on some slightly bigger things. And we've got a project that was just created called Java on Crack, which is a slightly strange marketing slogan, but it actually stands for Coordinated Restore at Checkpoint. And it's the idea of being able to freeze a Java application and then simply restart it again from that point. And that leads to very fast startup. Still very much in the early stages, but it's worth having a look at. Other people like Red Hat are heavily involved in OpenJDK as well, providing bug fixes and security patches and so on. And there are other companies like Amazon and various other ones as well. Now, how does that then result in us getting a distribution that we can install on our machines? Well, if we look at the Oracle JDK, what they do is they obviously take the source code and they use the same source code that's in OpenJDK. They will then build that and create their distribution, the Oracle JDK. Now, I put the arrows here leading directly from Oracle rather than OpenJDK. And the reason for that is simply that they use a different license. OpenJDK uses the GPL v2 with class path exception. Oracle use a different license for their JDK, which we'll talk about in a moment. Other people, like ourselves at Azul, do a similar thing. We take the source code from the OpenJDK, we may make some changes to it to enhance it a little bit, we'll build it, and then we'll produce our distribution of the OpenJDK called Zulu. Other providers will do a very similar thing. People like Amazon will take the source code, they'll make some changes to it, build Corretto, which is their distribution. And then you get other distributions, people like Opti-Num from the Eclipse Foundation. Slightly different here, where because they're not actually making any changes, all they're doing is taking whatever's in the source code repository, running the build scripts, and making that available to the people who want it. This is how we get our distributions. One of the things that was very significant when Oracle made this decision to move to a 6-month release cycle was they said it just wasn't going to be practical to offer extended updates for all releases. The way that we had in the past was that the current release had updates and then there would be a big overlap with the previous release. That wasn't going to be possible on a 6-month release cycle. And Oracle said, we'll introduce the idea of LTS, long-term support releases. And the way that they did that was they said that they would have a long-term support release every 3 years. And in fact, that's actually just changed last week. I should have updated my slides because Oracle have decided that they want to now have 2 years between long-term support releases. This is very similar to companies like Ubuntu who do the same thing with Linux. But the important thing to understand here is that this only applies to the binary distributions. It's not about the OpenJDK projects. OpenJDK, source code, people can continue to contribute as long as they want. But what we're talking about here is how long does a particular provider commit to providing updates to a particular release so that if you're using it in production, you can continue to have it as secure and as stable as possible. Now, when this happened, Oracle said that JDK 8 would be an LTS release. Because most people were using JDK 8 at that time, they thought that was very logical and they would allow people to continue doing that. What they committed to was to enabling people to use the Oracle JDK 8 for free in production systems until January of 2019, a couple of years ago. That only applied to commercial users. So in the case of JDK 8 update 202, that was the last update that was freely available for commercial deployments. If you're a personal user, you're sitting at home playing Minecraft, then you will still get updates for the Oracle JDK until the end of 2030. In terms of the 3-year release cycle for the LTS, Oracle said that JDK 11 would be the next one, and then after that, very logically, 3 years later, JDK 17. All of the other releases between there, so 9, 10, 12, 13, 14, 15, 16, they're all what are called feature releases, meaning they get 2 updates, and then when the 6 months expires and we move to the next release, Oracle will not provide any further updates to those versions. So we can see that we've got a clear pattern here in terms of releases that we're likely to deploy into production. Updates are the thing that most people are concerned about, because how do we get hold of them and what do we do with them in terms of maintaining that security and stability for our applications? So obviously, as I said, the Oracle JDK has these LTS versions, 11, 17, and so on. What we've seen is all the other providers of Java distributions, like Azul, like Red Hat, and so on, are following the same thing. We didn't have to. We could have decided to go our own way, and we'll kind of talk a little bit more about that, what we did to make some other decisions. But everybody is saying, yes, 11 is a long-term support release, 17 is a long-term support release, and it really just depends on how long people are prepared to provide updates for that. So the strategy is the same across all distributions. One thing that is different, though, is that Oracle released JDK 11 under a different license. And this had quite a big impact. The reason being that previously the license had been the Oracle binary code license. And that said you could use Java freely on your desktop, your laptop, your server. There were no restrictions. Only time you needed to do things differently is if you were doing embedded applications, putting it on a mobile phone or on a kiosk or something like that. Now with JDK 11, The license that Oracle have is the Technology Network License Agreement. And that says that it is still possible to use the Oracle JDK for free, but in a much more constrained set of circumstances. They said that you could use it for personal use, so playing Minecraft. You could use it for development use if you're running your IDE, if you want to do testing or demonstrations, all of that was okay. But the only places you could use it in production for an enterprise would be for Oracle approved products, such as their middleware or applications, or in the Oracle Cloud. Other than that, if you were running it in your data center or on your customer or your employees' desktops, then you would require a Java SE subscription, so a paid support contract. JDK 8 is a bit of a hybrid, and this comes back to what happened in terms of allowing personal use up until 2030. Oracle said that up until JDK 8 update 202, it's under the Oracle binary code license. After that, update 211, it's under the Technology Network License Agreement. So that means obviously that you can use it freely before that, and you have to pay if you want to deploy it into a commercial environment after that. That's quite important because if you are still using JDK 8 and you have downloaded updates from Oracle's website and deployed them into your estate, you may need to be careful about the licensing on that. Last week, with the release of JDK 17, Oracle decided to make things a little bit more complicated. So they had yet another license that they are going to use. And this applies only to JDK 17 or later. There's no retrospective change of licensing. And what they call this is the No Fee Terms and Conditions license, or NFTC. It's a very short license, and it really only has one line that describes what you can and can't do. But it's a little bit difficult to understand what that really means. And it's interesting that Oracle haven't been too sort of forthcoming in clarifying questions about, can I use it for this or can I use it for that? So as I put here, I can't spell no. No fee does not necessarily mean free. So you need to be very careful in terms of looking at the license and making sure that it applies in terms of what you're doing. Vulnerabilities in Java. Now let's talk about security specifically here. Security is a key thing when we're deploying enterprise applications. We need to make sure that any possibility of people exploiting these things is addressed as quickly as possible. And when Oracle decided to make these changes, they realized that there would be more people providing distributions, and they wanted to make sure that security wasn't going to be an issue. To do that, they set up a group within OpenJDK called the Vulnerability Group, and it's all the people you would expect. It's Oracle, it's Red Hat, it's IBM, SAP, Azul, and so on. And what we do as a group is we work together. We contribute resources in terms of engineering. We work on addressing vulnerabilities that are reported in Java, the platform. And what we will do is create those fixes. It won't just be Oracle's engineers, it will be Azul's engineers and Amazon's engineers and so on. Because we're talking about security here and potentially things that could be used to break into systems, even though this is an open source project, everything is kept private. We don't publish any of our email. We keep all our email between different companies encrypted. So there is no danger of people being able to see what's going on before we release an update that includes particular patches. Now, this is very good for us because what it allows us to do is to see what's happening in terms of the security patches before the update is released. We don't have to wait for that, wait for the change to be made to the OpenJDK source code and then start doing the work we need to do. So we're already looking at that for October, which is the next release, next update. And so that gives us time to take those changes, which are only made to JDK 17 right now, and then backport them to the older versions that we support. So we can go back to JDK 11 or JDK 8 or wherever. Having made those changes, we can then build the distribution that we want with all the different platforms, and then we can run what are called the TCK tests. I'll come back to that in a moment. What this allows us to do is to provide really what we could call an identical service to Oracle. So our updates are delivered effectively simultaneously with Oracle. Up until now, since 2019, we've had our updates available within 60 minutes of Oracle. I think the slowest we managed was 59 minutes, the fastest was 22 minutes. But that means that there's no danger of somebody being able to look at what's been addressed in that update, because all the details are in the release notes, and then try and exploit that between when Oracle release an update and when the update is made available for that distribution. Other distributions can be days, can even be weeks behind. People will say to me, well, Java's 26 years old. Surely we found all the security vulnerabilities there are in Java. No, that's just not realistic, because if you look at the source code, there's over 1.5 million lines of code in the JDK, and it just isn't practical to be able to eliminate all the possible security vulnerabilities in there. What I did here was to look at the highest scoring vulnerability of each update for the last few years. And the way that vulnerabilities work is you have a thing called a CVE, Common Vulnerability and Exposure. That describes what the vulnerability is. And then there's a common vulnerability scoring system that gives you a number that addresses how easy that vulnerability is to use and how dangerous it is. That works from 0 to 10. 10.0 is the most severe, the most critical vulnerability. And the red line here indicates when Oracle stopped providing free updates to JDK 8 and JDK 11. And we can see that even the first update after that, April 2019, had a vulnerability, critical one, with a score of 9.0. And the interesting thing about that is that if you dig into the details of it, it wasn't even a vulnerability in the Java code. It was actually a Windows library that was used to build the JDK. So these are the things we have to consider. Obviously, since then, we haven't had any more critical vulnerabilities, but we have had a number of high ones. And so it is very important that if security is any issue to you, which I hope it is, then you should be looking at this and thinking to yourself, we need to make sure that we apply updates, certainly where there's high or critical vulnerabilities, as quickly as possible. I mentioned testing. Testing is very important, and this comes back to what we were talking about in terms of the JCP and the Java specification requests. Now, Java specification requests, it consists of three things. This is what defines Java. So the first part is the specification, the virtual machine specification, Java language specification, and a list of class libraries. The second thing you get is the reference implementation, something that proves that the specification can actually be implemented. And in our case, that's OpenJDK. And then the third part is what's referred to as the TCK, the Technology Compatibility Kit. Technically, we should call it the JCK because it's the Java Compatibility Kit, but everybody talks about the TCK, so you'll see that. That's over 150,000 tests that you use to verify that what you've created in terms of the distribution matches the Java standard. And it will test everything in terms of libraries, in terms of the execution of bytecodes on top of the JVM, even to the point where you need to have a microphone connected to your test machine so that we can verify that the sound APIs work in the way that they're expected to. What this gives you is a very high level of confidence and assurance that if you take one TCK tested JDK and you move your application to another TCK tested JDK, it will work in exactly the same way. Can't guarantee that 100% because it's not exhaustive, but you get a very, very high level of confidence because everything is just going to work in exactly the same way, especially if you start from the same source code. Let's talk a little bit about what we do in terms specifically of our build of OpenJDK Zulu. So as I said, it's a build of OpenJDK. What we do is we backport all of the relevant security patches and bug fixes, and we can go all the way back to JDK 6. We have a wide range that we support in terms of versions, so 6, 7, 8, 11, 13, 15, and 17. We support more versions than anybody else, and that includes Oracle. All of our builds, with the exception of JDK 6, are TCK tested. Why is JDK 6 not TCK tested? Well, simply because now that Oracle don't support that version anymore, they've withdrawn the TCK license, and so we can't actually run the tests on there. But from the point of view of what we're doing, it is fully compliant to the standard. We just can't run the tests on it. We have very wide platform support. So if you want to deploy it on different types of machines, then we've got the obvious Intel 64-bit versions for Windows, Mac, and Linux. If you're using things like Windows XP, then we have 32-bit versions for Windows, and we have them for Linux as well. And then we've got things like Solaris on Spark and Intel, also got ARM32, ARM64-bit builds as well. Key thing here is that because of that TCK testing, it is very much a drop-in replacement for the Oracle JDK. No change in code, no recompiling, no changing command line flags. All you do, change your path, change your Java home, and run without any problem. We've had literally hundreds of customers who've done that, and we've never had any migration problems at all. CPU and PSU. This comes back to security, and it's very important to understand about how we can deliver updates. What we do is the same thing that Oracle does. We will provide you with 2 different versions of each of those updates. The reason for this is that the first type of update is called the CPU, Critical Patch Update, and really that's security only. All it contains is any changes that are related to vulnerabilities. And the idea behind this is that if you have a critical vulnerability, so a 9.0 to 10, and you need to address that very quickly, what you can do is take that update, test it with your applications, make sure they start up, make sure that the basic functionality is right, and then deploy that onto your machines to get those systems as secure as possible, as quickly as possible. The other type of update is the full update, or in Oracle speak, it's the platform patch set update. What that contains is all those security fixes plus everything else. So bug fixes, performance enhancements, other code changes. And comparing the CPU to the PSU, a CPU is going to be a handful of changes, maybe a dozen at most. The PSU will be hundreds, 300, 400, 500 changes is not uncommon in terms of an update. What that means is the chances that something might affect the stability of your code is greatly enhanced in that full update. Once you've deployed the security only update, make sure your machines are secure, then you can run some more tests on your applications, make sure that the full update doesn't impact anything, and then deploy that when you're happy. So the CPU is all about maximum security, PSU is all about maximum stability. Again, people will say to me, well, is that really important? Do I really care about this? And the answer is yes, you should, because we only need to look at July update last year. And in that, there was a fix to a problem that had been reported. Oracle created the fix, and that was all fine. But what they found after they released it in the full update, that some very common applications, things like Hadoop cluster, Solar, and Lucene, once that update had been deployed, those applications simply wouldn't start. They just wouldn't run at all. That meant that the fix needed a fix. And that took Oracle nearly 2 weeks to create, which then led to a delay because obviously providers had to then do the building, they had to do the testing and do the distribution. So there were several weeks between that update being made available and you being able to run Hadoop cluster, Solar, or Lucene on the full update. Had you had access to the CPU, then that didn't include that fix. So it only addressed security vulnerabilities. That problem wasn't in there. So it meant that you could have deployed that and kept your Hadoop cluster, your Solar, and your Lucene running. That had an 8.3 score in it, CVSS. And okay, it wasn't critical vulnerability, but it could have been. So this is why it's important to have both of those. And literally, if you look at the market, it's Oracle and Azul that provide both of those types of updates. Everybody else will provide you only with the full update. In terms of what we do for extended support, as I say, we commit to backport all bug fixes, all security patches from the current release to all of the ones that we've supported, and we do that across all of those. One of the things in terms of how long we do that is we have 8 years of active support, meaning that we do the 4 yearly or the 4 updates you get each year, and we'll do that for 8 years. And then we have a further 2 years of passive support, which is where we will not provide the regular updates, but if you do have a problem, you can report it to us. we will fix that and then provide a special update to you. One of the other things that we came up more recently was the idea of medium-term support. And this is where we can see that you're not restricted in terms of being a distribution to doing what everybody else does. And we said, well, with 3 years between LTS releases, maybe people would want to use some of the new features, between those releases. And so we said we will provide continued updates to JDK 13 and JDK 15, and we'll do that until 18 months after JDK 17 comes out, giving people to move from, let's say, JDK 13 to JDK 17. It's an interesting idea. We'll have to see how that works with the change to a 2-year LTS cycle, but it certainly helps our customers in terms of having greater flexibility of how they deploy their Java. The other thing we do is provide a full support service, a typical thing you would expect. You can report problems to us 24/7 by 367. We have a 1-hour response time SLA, depending on what level of contract you have, where we will acknowledge receipt of a problem. Can't guarantee to fix it in an hour. We'd love to be able to do that, but that's not really realistic. And if need be, we can have follow the sun problem resolution because we have 3 engineering centers around the world, and we can hand the problem over between the different teams. One thing that's interesting about that is that when I talk to a lot of people, they say, well, we've never had to use, the support service. So, does that really make a lot of sense? And I thought the same thing until I started looking at the things that people were reporting from our customers and realized that, yes, there are occasionally things that do have a significant impact. Our engineers will fix those and then we'll upstream it into OpenJDK. It's not things that are being reported in Zulu specifically, but things that are in OpenJDK. Okay, let's switch tack here and look at performance specifically with Java. So talk about Java microservices in the cloud. And this is where we talk about, the idea of how we are deploying our algorithms and how we can get better performance. Microservices-based architectures is very useful because we're breaking up our monolithic application into a number of distinct services. It's distributed computing in its sort of basic form. And we can have an example here where we've got our customers interacting with the cloud. We've got a number of services deployed, those interact with each other, and then we've got some kind of database to provide the data that we need. The good thing about this design is that if we find one of our services is becoming a bottleneck and all of the other services are interacting with it, which then degrades the performance overall of the application, rather than being limited in a monolithic application where we have to end up putting more resources for the whole application, we can simply say, okay, let's take that service, the one that's causing a bottleneck, and create multiple instances of it. We'll spin up more instances of that service, distribute the load using something like Kubernetes to orchestrate, and then we can reduce the bottleneck effect and have our application run better in terms of performance for the end user. So that's one thing that's very good about microservice-based architectures. But the other thing we need to consider, especially when we're dealing with Java, is that when our application is used by the user, they interact with that, and what they're seeing is their transaction. All they care about is they send a message from their web browser to do something, and they want the answer back. How that happens in terms of the individual microservices is not really of a concern to them, but it can be from a design point of view. Because if we're using Java and we have things like garbage collection going on, the latency of each of those services becomes cumulative, and we have to add them up. The more services we have, the more latency and performance impact we potentially have. So from a performance challenge point of view, it's this ability to spin up new instances. How long does it take to do that? How long does it take to get to the full processing speed? When we're using JIT compilation, we have to go through the analysis of which methods are being used frequently, compile them using the C1 JIT compiler, then recompile them using C2 JIT compiler or other things, and get to that optimum level of speed. And that takes time. Second thing is throughput. How much transaction processing can we get through a particular instance? And then the last thing we need to look at is this idea of latency. And what's the impact in terms of how long each of those services take when we add up the individual latencies, what problems could that introduce in terms of, extreme latency might actually result in us thinking that we need to restart a service even though we don't have to. Which leads us to the other part of Azul's business, which is a different type of JVM, Azul Prime. And what we do here is we said, okay, how can we improve the way that Java works? We did it for all types of applications, but it is very applicable to microservices and using algorithms. So we took OpenJDK as our starting point. We didn't want to rewrite the whole thing from scratch. So we used OpenJDK and we replaced certain things within that. Things that we replaced were to look at how to get better performance, how to get lower latency. Garbage collection is one of those things which is very problematic in terms of introducing non-deterministic behavior and long pauses. So we took all the garbage collectors you get in Hotspot, the serial collector, parallel collector, CMS, G1, and we removed all of them. We replaced them with one that we call C4. This is a truly pauseless collector, meaning that we can do all of the work of the collector concurrently with the application. So we do not need to pause your application threads in order to do the work. We can still move objects around within the heap quite safely. Second thing we did more recently was to replace part of the JIT compilation system. The old C2 JIT compiler was replaced with one that we call Falcon. That's based on LLVM, which is a compiler project, open source, and we've integrated that in to get better compile code, better optimizations. And then the last thing is ReadyNow, which is about reducing that warm-up time. Now, having made all those changes, to ensure that you don't have to recompile your code or change any of your code, we run all of those TCK tests to make sure that we are compliant with the specification. Again, it's drop-in replacement and doesn't have any problems. Looking at some examples of how this works, what I've got here is an Elasticsearch application that we ran on a machine, and we ran it twice. First time we ran it on Hotspot, second time we ran it with Azul Prime, and 128 gigabyte heap. The graphs we produce are looking at the latency of the JVM itself and the operating system and the hardware. So nothing to do with the application, it's just what impact the JVM has on the application. On the left, we can see a very typical graph in terms of GC pauses. So we've got lots of small spikes indicating pauses to the application. These small spikes are minor GC pauses, collection of the young generation. And then we've got two big spikes, much higher, which are major GC pauses, collection of the old generation. If we look at the right-hand side, the Azul Prime graph, remember that the big spikes is bad. So you might look at that and go, that doesn't look very good. I'm not convinced that what you're doing actually helps me. But I've been deliberately misleading here. And what I've done is I've actually set the scale of the graph to be different. On the left, with Hotspot, that's 0 to 8 seconds. Those minor GC pauses about half a second, major GC pauses about 6.5 seconds. On the Azul Prime side, I've scaled it from 0 to 80 milliseconds. If I change the scale of the graph to be the same, then we see the result. So this is the kind of thing that you show to your manager and go, look, GC just disappeared. There is no noticeable pause in terms of the application for doing its GC work. That's the kind of thing we can do with that. ReadyNow, as I said, is this idea of solving the problem of warm up. And so what we do here is we let the application run, we let it warm up, and then we collect a profile. So all the classes currently loaded, all the classes initialized, all the profiling data that was collected whilst the code was being compiled. And in terms of optimizations, there are these things called speculative optimizations, where we make an assumption that the way the code has run up until now, it will continue to work in that way. And we optimize based on that. Sometimes we make a mistake, things change, and we need to throw away compile code and recompile it. So that's a de-optimization. We remember all of the times we failed with that so that we can avoid that in the future. We can collect that information over a longer period of time, meaning we can wait 2 minutes, we could wait 2 hours, we could wait 2 weeks before taking that profile. And the other thing is we can do profiles for different workloads. You could have a Monday morning profile, Friday afternoon profile. What we then do is use that profile when we start the application again. Rather than having to go through the whole process of identifying methods to compile, compiling them and profiling them and so on, we use all that information and we say, right, before you actually get to main, let's load all the methods we can load, initialize all the methods we can initialize, compile all the code we need, and then make it run. So you get about 98% of the performance you had when you took the profile at the moment your application starts doing its work. Things like Lambda expressions are a little bit of a challenge, which is why we don't get the 100%. The effect of ReadyNow, and we can do generations of profile, is again with latency. We can see that in terms of the light blue line, we've got very high latency to begin with, where it's doing the profiling and the analysis of the methods to compile. Then when we use the first generation profile, we can improve that, and second generation profile, we get it almost down to being sort of flatlined. There is one little thing that we need to think about though, because if we look at a more generalized graph without ReadyNow, we can see that when we start the application up, we get low performance, then it gradually improves until we get our optimum level of performance. In the case where we do use ReadyNow, we get a much steeper graph. So we've done all that work and suddenly we can start getting that level of performance very, very quickly. But we get this kind of blank bit where nothing is happening in the application. And that's where we're doing that class loading, initializing, and compiling. So what we now do is, having looked at the way that our JIT compiler works, understanding that we're using LLVM as the back end of a compiler, that interacts with the VM by asking questions about how the profiling information is being collected and what that represents. And then it generates machine code based on that. So that's the way the compiler works. But we know that that's fully deterministic. So what we now do is take a full copy of all the code that was compiled as the application was run when we collect our profile. That way, rather than having to compile all the methods, we know that if the method hasn't been recompiled or changed and we've got the same profiling data, we can just use our compile stash, as we call it, as a cache, take the method out of there, and we don't have to run the compiler. What the effect of that is to reduce that blank period by up to 80% in terms of compile time, up to 60% in terms of CPU load. So we're getting almost that perfect graph in terms of performance. Just to conclude then, basically, I think it's safe to say that Java is as popular as ever. Certainly it's continuing to change, it's continuing to evolve, and specifically to address new types of applications. There are multiple choices of OpenJDK distributions, and it's worth considering carefully when you think about which distribution you want to use. What are the qualities that that brings to you in terms of how quickly you get the updates? Do you get both types of update? Do you have somebody to call if there's a problem? All of those things you need to think about. If you're looking for better performance without changing any of your code, then Prime JVM is obviously something that can do that because of the changes internally to the JVM itself. I will be very interested to see what happens in the next 26 years. I will be retired long before we get to the 50th anniversary or 52nd anniversary of Java. So I think that will be certainly interesting to see how Java continues to evolve. And with that, that's the end of the presentation. So I don't know if we want to see if there are questions that people want to take.
I see we have a question from Cornell. Cornell, go ahead.
Good morning, Simon.
Hi.
So my question is, so in a world where you're running your application in container, so for example in Kubernetes, you now have the problem that if your program shuts down, the whole pod shuts down. So how do you address saving that state or that profile and associate it again?
Right. Yes. So what we can do, because the profile is just a text file, and if you use the compile stashing, it's a binary file as well. So the way that we work around that is that you would run your application within the container, and you would actually generate the profile of the running application once you're happy that the service is running at the level you want it to. Then you can simply include that into the container so that the next time you start up the service, it already has that profile ready to use. So if the pod, as you say, shut down, you start it up again, but you've already got the profiles there ready to use. So you avoid a lot of that problem of the whole warm up. So it's very straightforward to actually be able to include those profiles into the container. We do that a lot.
So you could actually have, let's say, a separate load test suite where you hit it hard and you collect the profile, and then you can ship that, and then maybe if you want to take it further, find a way to get it out of the container and evolve it, but you don't have to. You can actually deploy a profiled application.
Yes, and again, you see, because the profile is very straightforward in terms of it's just a file. So what you could do, you see, you can either ship it directly in the container, or if you wanted to be more sophisticated, you could actually have a container where you basically access the profile remotely through a network connection and download that when you need it.
A volume or whatever.
Yeah.
Oh, so somebody's going to build a sidecar to do that.
Yes.
Okay.
Thanks, Cornell. Any other questions?
I do have another one. So, what is your approach or take on what's happening with Graal? Are you because I mean it's in a sense it's a diversion because it's ahead of time compilation. In a sense, you're taking the ahead of time and you're just squeezing it into the startup. But there's some other benefits on Graal in terms of memory layout and things like that. Do you do anything different in memory layout? Are you looking at ways of leveraging Graal in the future?
Yeah, so Graal is, as you say, it's a very interesting sort of piece of technology, but they've taken quite a different approach to the way that we do it. And as you say, it's the idea of ahead of time compilation versus just in time compilation. Now, ahead of time compilation, as you say, gives you some real benefits in terms of both the startup time and also the footprint of your application, because you avoid a lot of the stuff that's required for the JVM, and you avoid all of the warm-up phase and everything like that. So if you're using microservices where it's typically some kind of AWS Lambda or serverless computing, a function, if you like, then that makes a lot of sense, because you're going to be running it for a very short space of time. You don't really care about garbage collection. You don't care about the sort of overall level of performance. It's just get it done very quickly. But if you're running a microservice where you're more concerned about that service running for any period of time, then AOT will give you less overall performance. There's various optimizations that you can't do with static compilation that you can do with JIT compilation. Now, even though Graal uses profile guided optimization, which is kind of like what we do with profiling, and then feed that back into the compiler to make it generate code that's optimized to a specific run of the application. That's great, so long as your application doesn't change in terms of the way that it works. With the JIT compiler, obviously, if it does change, we can recompile and adjust to that on the fly. Can't do that with Graal. But coming back to your point about memory layout and optimizations in that sense, yes, it's something that we have been looking at a lot because of the way that C4 works, the garbage collector that we use within Prime. We do some things specifically around that to optimize around layout and so things like that. We also, the way that Prime works is that it only runs on top of Linux. The reason it only runs on top of Linux is because we either use our own kernel module, or we use some more modern system calls that allow us to handle the allocation of memory in a way that's better suited to the JVM than the standard Linux virtual memory system, which is designed for general purpose applications. So we do a lot of stuff to try and be clever about how we handle memory allocation and garbage collection.
One more. I saw there was a JEP where they're looking at reducing the size of the object header.
Mm-hmm.
Is that something that you're looking at, or maybe already doing something in that space?
Yeah, I mean, compressed object headers is something that's been sort of around for a while. In our case, it's not something that we are actively trying to do with Prime. If anything, we want the object header to be bigger. The reason I say that is because the problem that we suffer from is we need a lot of bits in the object header to indicate the position of the object in the heap. At the moment, we can scale up to a 12 terabyte heap. And so we need more bits because we have customers who would like to go beyond 12 terabytes in a single heap. Can you believe? But that's the issue that we have with that. So compressed object headers for us is not really something that we're working on directly.
Okay. Yeah, well, I can see because I hear people always, no, I'm going Graal, and then I'm like, well, if you're an IO-bound application and resource constraint, then great, do it. But if you want speed, then the JIT's gonna hit you over the head in 5 seconds, and then you're in a different order of magnitude. So
yes,
I imagine for what people interested in doing heavy math and stuff would benefit from the JIT all the way.
absolutely.
I have seen some interesting improvements in Graal in some of the simpler code, but it still doesn't come close to the JIT. It does beat out a lot of things, even Go in many cases, which is making some people sad. But yeah.
Yeah, one of the things that, especially with our the Falcon compiler based on LLVM, what we get from that is much better optimizations, and from a numerically intensive type of thing, that we get real big benefits because we can use vector operations in much wider set of circumstances than you can with Hotspot and C2. They have introduced the vector API in JDK 16, which allows you to sort of force it to use vector operations. But most of the time we don't need to do that because the compiler will actually recognize where it will use vector instructions and apply those. I think we're running out of time, aren't we?
Yeah. I was about to sort of jump in and say, Simon, thank you. If there are no further questions, or if there are further questions, please feel free to either drop them in the chat now, or if you'd like to, we will be sending out a copy of the slide notes that Simon has presented today. And so you're welcome to just reply there, and we'll make sure that Simon can answer them for you. Simon, thank you very much for that. I think I started this by saying, Simon talks a lot, and the stuff he talks about most passionately is Java. I think in the last hour we've seen a lot of that, and I think seen some of the in-depth knowledge that goes into making sure that these Java platforms can be trusted and can be performant. Simon, thanks very much for your time, and to all the attendees today, thank you to you for making yourselves available to listen to this presentation, and we welcome any questions that you might have after the session.
Great, yes, thank you very much, everybody.
Thank you, everyone.